Angles in the measure. So we're going to take a look at how different angles are created on a Cartesian plane and a new system of a new unit for angles instead of just using degrees. But let's start with the Cartesian plane and see what you know about it. So first of all, we need a Cartesian plane. So here's one. And I guess the very first question for you to even think about is, why is this called the Cartesian plane? Some of you may know and some of you may not, and it has to do with history. So we'll come to class and that'll be our first question, and I can give you a little history lesson. But this is called the Cartesian plane, and here's some information you need to know about it. So first of all, there are four sections to the Cartesian plane, and they're known as quadrants. And I'll mark them in red. This is the first quadrant, the second quadrant, the third quadrant, and the fourth quadrant. And they are dividing up the Cartesian plane by looking at the different four sections created by where the axes are, the x-axis and the y-axis. On the Cartesian plane, we have a very special segment of the x-axis, this piece, that's known as the positive x-axis. And the reason that it's special is because that's where we start to measure angles from when we start to measure angles in these quadrants. And so we have another part that comes up like this. It has a special name. It's known as the terminal arm of theta. And theta is the angle created between the terminal arm and the positive x-axis. And as we move the terminal arm, we get new angle measurements. So if we move the terminal arm to go to the y-axis, we end up with 90 degrees. If we move it back down this way, we end up going smaller and smaller, so this is really 0 degrees. If we go past the y-axis and over to the negative x-axis, we end up measuring an angle of 180 degrees, and if we get these huge angles, we end up going to 270, and all the way around this direction would get us to 360 degrees. And some of this you may have seen in the past. But we definitely need these definitions and to be able to speak this language for this unit as well. If instead of swinging my terminal arm counterclockwise, I instead swing my terminal arm clockwise, I end up creating a theta that's going in the other direction. And that's fine. It's just known as a negative angle. So positive angles are measured counterclockwise, and negative angles are measured clockwise. So let's take a look at an example of a question that can be asked of you already. And that would be to draw an angle of negative 100 degrees. So here's my sketch of my Cartesian plane, and I have to go negative 100 degrees. Well, that would be negative 90, and then I go another 10 degrees past that. That would leave 80 degrees on this side, between here and here. This is 10. So this angle here, which I'll call theta, that would be negative 100 degrees. If instead I were asked to draw an angle of 400 degrees, what would that look like? Well, 400 degrees would mean I go positive, there's 180, and I keep going around. There's 360 that I've gone so far, but I have to keep going. I have to go another 40 degrees. And so my angle, theta, would be this weird angle that's spun all the way around like that. Now, we do actually see this in real life, angles bigger than 360 degrees. I wonder if you can think of any sporting events where this actually happens. Maybe bring that to class as well and see if you can figure out some places where that might actually happen. So you can have these angles that actually go bigger than 360, smaller than 0 degrees. You're just spinning in different directions. And this is a great point to introduce this idea of what's called a coterminal angle. And a coterminal angle is an angle, or actually coterminal angles are angles that have their terminal arm in the same location. So in green above, the angle 400 degrees which spun all the way around to 360 and then went another 40, is coterminal with the angle of 40 degrees. Their terminal arm is in exactly the same space. In blue above, I had that negative 100 degrees. So negative 100 degrees above is the same as, and I'll just draw it in red so we see a different color, if I went around this way and ended up here. So that's 180 to this point, and we said another 80, so that's 260 degrees positive. Now, coterminal angles are pretty interesting because there's quite a few that can land in the same spot. In fact, there's an infinite number that can land in the same spot, and let me show you what I mean by that with this next example. Okay, so we're going to find some coterminal angles to 80 degrees. So 80 degrees is an angle like this, 80 degrees, and I want to find some coterminal ones. Well, really all I have to do is spin around one more time. And so coterminal to 80 degrees could be 80 degrees plus spinning around one more time, which is 360. But then I could spin around another time, so another answer to this would be 80 plus 360 times 2. And I could spin around as many times as I want. So I could times it by 3, or times it by 4, or times it by 5. So I could times it by n. So a general solution to this might be times this by n. And watch this, I can actually take my terminal angle, and instead of going positive, I could go negative, and that would be backwards 360 degrees. Well, the easiest way to get it to be going back 360 is to multiply it by negative 1 or negative 2 or negative 3 or negative 4. And so the n value, to just quite simply make it a positive or a negative, I'll just define my n value is an integer. And then I can multiply it by 1 or 2 or 3 or 4 or 5 or negative 1 or negative 2 or negative 3 or negative 4 or negative 5. So then I can say, here's the answer to all the coterminal angles to 80 degrees. There aren't any others. 80 degrees plus or minus, and the minus is taken care of by the integer, 360 degrees each time, n number of times. Okay, now we're really going to switch gears and take a look at a new kind of angle measurement. Radian measure. And this is probably one of the most important aspects of Math 12 to take away, is the idea of radians. So far we've used degrees to measure angles, but there is actually another option, the radian. A radian is a measurement of the arc length of a certain angle on the unit circle. So let's take apart this definition a little bit. First of all, we need a unit circle. Cartesian plane, circle, and a unit circle has a radius of 1. Which means that it goes to 1 this way, it goes to 1 this way, it goes to negative 1 this way, and it goes down to negative 1 this way. Now, by the definition, a radian is the measurement of the arc length of an angle on the unit circle. So let's just notice something interesting about this. If it's a measure of the arc length and I draw a complete circle and I calculate the entire arc length, it looks a little bit like this. Unit circle, arc length that goes all the way around. So my degrees of theta goes all the way around. Well, we'd say that's equal to 360 degrees. But now we're talking about the arc length. And the arc length is, how far did I go around the circle of radius 1? Well, I did the circumference. And the circumference has a formula. It's 2 pi r. In this case, I even know my r. It's 2 pi times 1. So the circumference is just 2 times pi. Which means that the distance around the edge of the circle in arc length, which is in radians, because radians is a measure of arc length, is 2 pi, which means that 360 degrees is the same as 2 pi in radians. Well, that means I can convert some other things. Let me just give myself a little bit more space here. If I only go halfway around a circle, then I only go 180 degrees. So the arc length is only half 180 degrees. The arc length is only half of half of 2 pi, which is 1 pi. And if I only go a quarter of the way around a circle, and I measure the arc length, well, a quarter of the way is 90 degrees, and that's half of 1 pi, which is pi over 2. Whoa, there must be a way to convert this much more quickly than having to just kind of guess and check this. And there is. We can use the ratios, and then we can use some formulas to convert. So let's take a look at that next. To convert between degrees and radians, there's two different formulas that we can use. The first one is if we have degrees and we want to go to radians. So what we do is we multiply however many degrees we have by pi divided by 180 degrees. We'll do a couple examples of this in a second. Number 2, if I want to go from radians to degrees, I do multiplication by the inverse. So I now multiply the radians, by the reciprocal. So I now multiply the radians by 180 divided by pi. And as promised, a couple of examples. So if I have 17 degrees, how do I make that into radians? Well, first of all, I take 17 degrees and I multiply that by pi divided by 180 degrees, and you'll notice that the degrees cancel each other out, and you get 17 times pi divided by 180, and if you want to estimate what that's worth, you can grab a calculator and do that. And to 2 decimal places, it's 0.296, so that rounds up to 30. Let's take a look at another example of this. If I have 3 pi over 16 and I want to change it to degrees, I take 3 pi over 16, I multiply it by 180 degrees over pi. Luckily for us, the pi's cancel, and I have to do 3 times 180 degrees divided by 16 on my calculator to get 33.75 degrees. And one last example for you. And these are the ones that people find tricky. 1.15. Is it going to degrees or is it going to radians? Well, does it have a degrees symbol? Because if it has no symbol, it's in radians. So no symbol means you're in radians, which means I want to know how to make this into degrees. That's the hardest part of these questions. Once you know what you're converting between, then you just do the conversion. 1.15 times 180 degrees over pi. I can do all of that on my calculator, and I'll round to 2 decimal places, and I get 65.89 degrees. We'll be working with radians and degrees and converting back and forth a lot this year, so we'll definitely need some practice with all of this. Okay, one more section for you and then we're done. Arc length. With this linked to the definition of radian measure, it's possible to use radians as an angle measurement to calculate the arc length of an angle, which kind of makes some sense. There's a formula for it. A equals r theta, and these are what A and R and theta stand for. A is your arc length, R is your radius, and theta is your angle. So if you've got a circle, and it doesn't have to be a unit circle, and you know the radius and you know the theta, you should be able to use it to calculate this arc length, and that's how you use it. So here's one example. What's the radian measure that subtends an arc length of 10 centimeters if the radius is 4 centimeters? Well, I threw some crazy vocab in there, subtends. Look it up in a dictionary, see if you can make sense of that. I really don't even need to know what it means. I need to know the formula. I need to realize that the arc length is 10. I need to realize the radius is 4, and I'm solving for a radian measure, which is theta. So I divide both sides by 4. 10 divided by 4 is 2.5. So that's the answer. It's 2.5 radians that subtends an angle of arc length, subtends an arc length of 10 centimeters if the radius is 4 centimeters. Done.